Okay, so welcome back for the afternoon session. And our first speaker is Camilla Nobili, and she's going to talk about looking for the Batchelor scale.
Okay, so thank you very much to the organizer for this beautiful opportunity to talk here. I'm very excited, first time in Cambridge, and I apologize for the confusion about the title. So my previous title was Bounds on Mixing Norms for Advection Diffusion Equation in the whole space by Fourier-splitting and decay characters. But yesterday I was talking with my moderator Andrea, and he said it's too long. So now this is the title. So it's the same talk though. So I would talk about exactly the same. All right, so this talk is about one of the latest Charlie's vision, and it's a very difficult problem, but nevertheless, I'll try to introduce you to some so to the topic, so which is mixing. Although Michele already said a lot about the problem, but since I will take another direction, I'll have to reintroduce things, and then I apologize if the beginning is a bit boring, but so this is the outline. I will talk about the rule of, so first I will introduce the problem, and then I will talk about the role of steering in mixing. Then I'll introduce the main motivation for my work, which is the smallest scale of mixing, so understanding or capturing the smallest scale of mixing. And so in the third part, I would really talk about some new results in this, motivated by this vision of Charlie. So let me start by the classical picture. So when you want to describe mixing, which is so dropping ink into water or some other fluids. So you have this concentration red over white, and so a good so this you will reach mixing when the concentration so when there will be a sort of homogenization of this ink in the water, so you will get a sort of mildly red color, you know, homogeneously in this fluid. And okay, so mixing is can be described as by two main mechanisms. One is molecular diffusion. So at the molecular level, you have this frantic motion of particles due to temperature. And then you have so there is this net flux from region of high concentration to regions of low concentration. So this is at a molecular level, while steering is about transferring mass from low to high wave number modes and is creating filamentation. Now, while molecular diffusion is described by the heat equation, steering can be described by the pure advection equation. So dTF plus U grad F. So in this talk, I will always, even if I don't tell it, so for me, U is a divergence-free vector field. And then you look at this beautiful picture that I took from Doering and Meitz. This is one of their simulation, in which they start with a concentration black over white. And then they choose a particularly smart field. And then you see that this concentration is advected, and then you see the creation of this filamentation that gets stretched longer and longer. They become thinner and thinner, and then you see that at some point, so for large time, you'll get this configuration in which you can't distinguish scales anymore. So it's really a gray scale. So have in mind or try to memorize this picture, because now we add the diffusion. I hope this noise is not from me, right? No. Okay. Me? But like, can someone please mute the microphone? So Or maybe Andrea, you can write a message from. Okay. I think it's off. All right. Okay. So now this is the picture without the diffusion, and now let's see what happens when we actually add diffusion. So it's exactly the same experiment. So concentration black over white, the steering field is exactly the same, but you see that so at a qualitative level, it's more or less the same, but you start to see immediately that the picture is blurred. And then you see what happens at the end. The end is not uniform like we had before. So at the end, we had a grayscale, while here, you clearly see that there is still a typical length scale remaining. And so this is starting, so this starts to go in the direction of what I want to understand, and this is the minimal scale of mixing. But nevertheless, I want to take it slowly. And I want to try to tell you what the rule of steering is, because there is a lot going on in this field, and there are different problems. And at some point, I'll try to unify also, or to make some observation at the end, compared to other problems and other approaches. So let me take it slowly. So advection diffusion equation, you can take the torus, two-dimensional torus, or you can take any regular set with non-flux boundary condition. And then you see that if you take the time, so remember U is divergence free. So if you take the volume averages, then the ddt of the volume average of T is equal 0. Okay, so then what makes sense to do is to say, okay, well, let's write down T as the sum of the volume average plus some fluctuation theta. And you see that now the equation, the function theta is satisfying the advection diffusion equation, and now is 0 average. So this is the equation I will be looking at, because then you understand that if I look at this quantity, which is the volume average of theta squared, which is exactly this difference squared, then this is measuring the distance of T from its average. And this is a measure for mixing. Now, if we look at, if we accept this as a measure for mixing, clearly the first thing you want to do is to write down an energy estimate, an energy identity here. Here everything is linear, so you write the identity, and you find the evolution of the concentration variance, which is ddt, the volume average of theta squared, equal this right-hand side, where you see that there is a -2 kappa times the gradient, which means that on one hand, the molecular diffusivity is there and it's necessary to make the concentration variant change, because if kappa would be 0, then we would have conservation. While, so when you look at this identity, you see that the steering flow is not there. So it's not that it's not there. In this identity seems to not be there, but clearly it's changing the gradients there. Okay, so nevertheless, this fact that U drops out when you especially do this, you work with generic flow, is a little bit, let's say, not optimal. So we will talk about not this question again. Well, okay. So let me now go into the question. So how does steering act? So does it amplify mixing? For answering this question, so I just brought down an example. So first I started with the heat equation, and I consider an initial data which is sinusoidal. And then, okay, so you can compute the solution. So based on this, given this initial data, you can compute the solution, and the solution is this exponential time the sine. So if you teach Fourier analysis class, this is the class, so the things you do all the time. And then you see, so this, so when you write down then the variance, you see that it decays exponentially, okay? And the rate is the one written in orange, so it's proportional to the diffusivity and inversely proportional to the square of the length scale in the density variation. Okay, so it's written there. Now, let's consider now a very simple choice, which is the classical shear flow. And let's take an initial data. So we are in 2 dimensions. We take the initial data, which is A times the sine of kx, so in one direction. And you see that, so the shear flow and the initial data are perpendicular. So what happens is that, exactly, so these are the level sets of the initial data. And this shear flow is tilting the level sets. Okay, so you go to write down the solution, and this is what you get, which is again a sine times an exponential. Things have been changing because you see that there is a transfer of density, so we go from initial length scale of order 1/k to scales which are definitely smaller. Okay, so of order k times the square root of 1 plus s squared t squared. Clearly, this parameter s is the one in the definition of the intensity of the shear flow. So, I mean, what I want to tell you with this example is that now if you compute the variance, you get an exponential, but this time is amplified. So this exponential is faster. You see, because, I mean, exactly the shear flow appears with a minus sign. So you have minus 1/3 s squared t cube times 2 kappa k squared, which clearly now shows you that this exponential has been accelerated. So now this is to say something that probably many of you have seen this example. It's just, I apologize if I'm taking it slowly. But just to tell you, so shearing, so the steering is important. As you see, it's enhancing the exponential decay. And then, so I wanted to just put this remark that I found in the notes of Jean-Luc Tifo, in which he was saying to students, if I remember correctly, in some lecture notes. So what is the time to heat up a 10 square meter room? And then if you do the computation, given that the kappa is this very tiny number, then you see that the diffusion time for a 10 square meter room would be 53 days. So as Jean-Luc says, you better stir. Okay. So, all right. So this is just to say, so this is the first point. So we have a measure for mixing. I now didn't discuss whether it's a good measure or not, but this is the variance. And then we see the effect of mix, so the effect of steering on mixing. Okay, so now we have these 2 phenomena. So on the one hand, we have that any good steering is creating this filamentation. So these filaments get stretched, and so by incompressibility, this gets stretched longer and tinier. But because we are in presence of diffusion, and this is clearly now a difference compared to the talk of Michele, we have the diffusion always acts by spreading this filament. So it's in a sense that they start to compete, these 2 mechanisms. And again, this is the picture of Charlie and Christopher Miles, and it's very illustrative of this. So this is now entering the topic, which is the minimal scale of mixing. And this is a remark that Charlie told me, and I find extremely important. So Charlie was telling me, look, effective steering can happen also in mildly turbulent flow. You don't have to have turbulence to have effective mixing. And he gave me this example. So take a pure strain flow, and you take a blob that gets stretched. So the blob in the origin, and due to the action of this pure strain flow, this gets stretched on the x-axis. And then you can write down the Batchelor scale as the physicist would write it, lambda b is the kappa divided by gamma to the 1/2. Gamma is right, is in the definition of the pure strength flow. Okay, so this is quantifying the Batchelor scale. And now, as turbulence is not maintaining itself, we have to write down the energy. So we write down this the energy dissipation rate per unit mass, and we call it epsilon. And then now we identify gamma, the strain, with the energy. Okay, and now by the definition above, you have this is epsilon divided by nu to the 1/2. So now because of this identification, now you can write down the lambda b, which is the Batchelor scale, as kappa divided by nu to the 1/2 times this ratio, which is nu to cube divided by epsilon. Okay, so now the first one is the Prandtl number, actually the inverse of the Prandtl number. The Prandtl number is nu divided by kappa, and the other one is called the Kolmogorov scale, and we call it lambda k. Now, if you think the Prandtl number to be very large, for example, for thick oils and glycerin and other fluids with a very high Prandtl number, then you see that the lambda b would be much, much smaller than lambda k. So in particular with this, Charlie was telling me, look, I mean, you don't have to go to high Reynolds number to see effective mixing, but this can actually happen also at small Reynolds number. Okay, so I thought that to include this because I find it always a very important observation. Now I repeat a little bit what Michele was saying. So unfortunately, so at the beginning, not unfortunately, but we started with a measure of mixing, which is the variance. But again, the variance, again, especially when you look at the things like you want to quantify a scale, it doesn't seem the correct the measure. So the correct measure was identified by Matthew, Matzik, and Pottel, and is a measure that downplays the rule of small scales. And this is the H-1 norm. As Michele said, this scales like a length.
Hi, how are you? Okay, fine. I have a few minutes. Yes, I mean 10 minutes or something, yeah. Okay, bye.
Hi, Edris.
Hello?
We can hear you.
Oh, sorry.
Okay, so so what I was saying is that the good thing of this measure is that it captures both homogenization on one hand and filamentation on the other hand. So now in the case of advection diffusion equation, so in presence of diffusion, actually we have to take a quotient. Again, this scales like a length. This norm is not conserved anymore, differently from the case of Michele. So we look at this quotient, which is the H-1 norm squared divided by the L2 norm squared of theta. So now we call lambda the filamentation length. And so Charlie has, together with other authors, has been looking recently at this mixing with diffusion, and there are very interesting results. So at the theoretical level, he computed bounds both for a dyadic model. So he created a shell model that was capturing the right features. I will not talk very much about it, but he also really derived some theoretical results in which you see that the filamentation length is bounded from below by an exponential, though these results are not optimal. Okay, so but the most revealing part are these numerical simulations. So look what happens when they do this local in time optimal flow simulation. So they see that for Peclet number, the Peclet is 1 over kappa. So 1 over the molecular diffusivity. So you see that what happens when Peclet is non-zero is that at some point for large time, you reach a plateau. For long time, so you have the decay due to steering, and then eventually you seems to reach a constant. And these are really revealing numerical simulation. And now the vision of Charlie is to show that lambda, so this quotient, for large time converges to the Batchelor scale. Now, this is a very hard conjecture. Actually, Charlie never really talked about conjecture. He always said, I have a vision. So it's very hard to prove. First of all, because so in general, so analytically, what you can find is, first of all, finding upper lower bounds. In general, for this type of equations, lower bounds are very difficult to find. So think even just finding the lower bound for the L2 norm of theta. And then there is the other fact, which is crucial, is that in order to see that this quotient goes to a constant, clearly you have to have exponential decay at the same rate, which is absolutely difficult to get into a paper. Right, and will this vision hold for any given flow, or there are some smart flow for which this happens? This is also a question that we don't know yet. And it seems strange, but even on the torus, which generally is the first example, when obviously you want to work on bounded domains, but in order to simplify your life, you take the torus, and even on the torus, it's very hard to just compute this norms. On the torus, the difficulties. So let me say very roughly, it's like the energy is coming back in. So you have always this difficulty on quantifying the scale because of this phenomena. But so why I'm talking about the geometry is because we have been really looking at the torus, and we have tried with the Liddell-Paley type decomposition and fancy type of regularity estimate, Caccioppoli, and so on. And then at some point we had to step back because we didn't get what we wanted to have. We also had difficulty of finding reasonable lower bounds. So we stepped back and we said, okay, so what happens on the whole space? Let's remove the boundaries. And this is motivating now the work that I've been doing with Stewiąn Pottel on this. And so the crucial thing, so the step number 0 is that, okay, so if you want to quantify this quotient lambda, you have a beautiful interpolation estimate. Now, how can this interpolation estimate help you? Well, because it relates this quotient to this other quotient, which is L2 divided by H1, or grad of theta in L2. And now the question is whether we can find a lower bound here and an upper bound on the gradient, and then just see whether something is getting stuck. So at the beginning, we didn't have much of an intuition whether things should really get stuck in our end. So this is what so our goal, the goal in order to succeed in seeing this vision of Charlie would be to see lambda getting stuck to a constant. Now, I tell you a little bit on of the heuristic argument that brought us to this result. Is okay. So when you're on the whole space, you can do it also on the torus clearly, but you can. It's very convenient to divide theta in a part that satisfies the heat equation and the other part that is satisfying the difference. Clearly now, if you have this decomposition, so you can get easily a lower bound when you subtract the L2 norm of eta to the L2 norm of H of the heat equation. It's as simple as that. So this was the main, so the ideal number 0. Now, if you have reasonable condition on theta 0, it's very easy to find a lower bound for H, so for the heat equation. And so believe me, I will anyhow explain later. And then for doing the rest, we can use the, representation that we have. So we can see the theta as perturbation from the heat equation, and write down this representation in which you see that the Green function is convolved with u grad theta. Okay, so until here nothing particular is delicate, but then you see that in order to find an upper bound on theta, and why do we need an upper bound on the L2 norm of theta? Because at some point we have to quantify the L2 norm of the difference. And clearly these two are related. So nevertheless, we had to put some condition on this velocity field in L2 in order to find a decay bound on theta in L2. Okay, so this is more or less schematically what's happening. So what is the heuristic? So on one hand, the lower bound for the heat equation and an upper bound for the differences. And then eventually, this is not the hardest part. So it's to find, so once you have all this, finding an upper bound for the grad. And then by interpolation, you have everything you need. All right, so now it might seem that for the whole space, everything is known, everything is clear how to do these estimates, but I tell you that you don't really have a representation formula that is nice and clean with which you can work. Obviously, many people have worked in this in these topics, like trying to find the representation formula or green functions. I cite, for example, the work of Mayakawa, Carlen Loss, and others. But the approach we took, we think is very smart. It's called the Fourier-splitting method. This method was first introduced by Maria Schoenbeck in the 85. And it's based on this very simple idea, but very powerful, to split the frequency space in two parts on a ball, which radius is decaying in time, and the rest. And then you write down this energy estimate, which is weighted. Is a little bit untypical to see like this, where you see that on the right-hand side, this theta hat is, so the integral is computed over S of t, and S of t is, again, this decreasing bolts in the Fourier space, decreasing in time bolts. All right, so given that, we can use, so by this Fourier-splitting method, we have to pass through this representation formula. And again, I noticed that on the right-hand side of this representation formula, because we see theta as a perturbation from the heat equation, so you see that there is this product u grad theta that we have to bound, okay? And again, so we will have psi times theta in L2 times u in L2. Now, obviously, I will not go into details, because then probably, as you can imagine, I will start to do an iteration techniques. I start by the maximum principle for theta, then I take the result and I put it back from at the beginning, and then I iterate like this. Nevertheless, I don't want to go really into details because it gets very technical very quickly. But what I want to tell you is that you see that u in L2 appears there. Now, what happens is that so we would have to impose a decay of the type 1 plus t to the minus alpha to get the claim, when an alpha has to be bigger than 1/2. So if I don't specify anything and I just use this naive approach by starting by the simple bounds of the heat equation, then I get exactly this result. Now, as I will comment at the end, this is a bit too restrictive. So this tells you that U has to decay for large time, and actually with a certain power. So alpha has to be bigger than 1/2. So somehow I would see, you would see later that I would relax this. Now, this was about the Fourier-splitting. The Fourier-splitting is a very smart method for finding upper bounds for theta in L2. Then the other problem is to find lower bounds, which is also here. You see, it looks very easy at the level of the heat equation. In fact, I mean, if you have just the heat equation, then you could say, well, okay, so just choose initial data for which the Fourier transform is bigger than m on a ball of size delta, so on a very small ball. If you just put this condition on the initial data, then you get a lower bound easily, because you have the representation formula. So you have theta 0 times this exponential. You plug in this condition, and then you have your bound. It's a matter. So this is a matter of a second. Now the problem is that you see that this initial data is excluding, for example, mean free data. So it's a pretty, it's a very small class. So this is allowing you only to take Gaussian-like initial data, because you can't be 0 at the origin in Fourier space. All right, so now here it comes this improvement of the whole paper that came by trying to think about better initial condition. So at the beginning, we had this approach by this smart method of Maria Schoenbeck that was just working. But then we had two restrictive conditions on both the velocity field and the initial data. Now, what I'm trying to tell you now in this last few minutes is that actually, if you choose smarter initial data, things happen and they improve the situation pretty much. Now I show you why. So we relax the assumption on the initial data, and we use the so-called decay characters. So I read the definition. So the decay character is the unique R between -d½ and infinity, such that this integral, this weighted integral, is finite and bigger than 0. Okay. So in particular, so the unique R such that this holds is called a decay character of the initial data. And in particular, I mean, this example is very illustrative, because you see that essentially the decay character is telling you, or is quantifying, how fast is the initial data going to 0 in Fourier space. And in fact, if you say, okay, so suppose that you have an initial data, it goes like psi to the alpha in modulus over a small ball, then the decay character would be alpha, the power alpha. Now, so if you consider decay character, so an initial data with decay character R star, and you just consider the heat equation, you see how the long time behavior of the solution is determined by this initial data. So clearly, so if you would not have this restriction and you take just L2 initial data, you would not have any, so you would have that the decay is -d/2. But instead, if you consider this particular decay character, so this class of initial data, you see that something is changing at the level of behavior for long time. So the long time behavior in time of solutions is determined by the small frequencies of the initial data, right? And so this decay character, I mean, they are also new to us, so to me, I would say. But in the literature, they have been used by Schoenbeck, Nietzsche, Brandolese, Planas, Bjorland, and these always in the context of understanding long-time decay of a solution for different equation, including Navier-Stokes. And the reason why probably we could succeed so fast in using changing everything, is because this decay character have been used by Steffen in characterizing Feynman graphs. So I am absolutely not an expert, but apparently they are there and they are used by theoretical physicists in a renormalization quantum field theory. So it was extremely practical using this decay character. So, all right. So just to conclude, I don't want to just bother you with a lot of different like estimates, but also because they become a little bit more technical, but you see that we could find upper and lower bounds for theta in L2. You see that, okay, so here the upper bound looks a little bit more complicated because this is the presence of the decay character that is so changing a little bit the powers there. But nevertheless, we get upper and lower bounds for theta in L2. And then obviously, so now I'm not telling you the whole story because it's bounds over bounds, so lower upper bounds, and also we have to get upper bounds for the gradient. Obviously, I don't want to enter in the detail, but you see that there is at least one region of alpha for which we have a sharp result. So that is exactly, so remember that alpha is the power of u, so how u decays in time. So in this, for alpha bigger than this number, so again, this is the behavior of u for large time, you get that this is sharp. Okay. Now, to conclude, this is the theorem. So I hope that I managed to convey the fact that lower bounds are difficult. And this also in this paper, eventually find that the lower bounds for theta clearly was probably the most intricate part. But nevertheless, this was then the solution to this problem in Rn. And we found exactly that if u in L2 decays like this function, 1 plus t to the minus alpha for some alpha, and the grad of u in L infinity decays like 1 plus t to the minus beta, then the quotient is bounded by 1 plus t to the 1/2 times f of t. I don't want to tell you what f of t is. It doesn't really matter. So the important thing is 1 plus t to the 1/2. I'll tell you why. So the f of t is a function for which if you are, so if beta is bigger than 1, you are going to plus infinity, so you have dispersion. But if beta is between 0 and 1, actually this guy is going to 0. So the f of t determines whether you go to infinity or to 0. So to wrap up, in Rn, nothing gets stuck. Either you mix or you don't. So the other thing, so let me look at this very quick computation that I did. So that I did at the level of the stochastic heat equation because it's way easier. So if you look at the stochastic heat equation and you do the very simple, I mean, you apply the Ito formula to find the variance, you see that the variance of the stochastic, the solution of the stochastic heat equation is 2 kappa t, which is exactly in line with what we proved. Okay, so this is exactly the 1 plus t to the 1/2. So this is consistent with the heat equation. Then the other thing I wanted to tell you is that, and this is what surprised us, is that we could actually show decay of the lambda even when u is not actually decaying. So if you look at the u in L2, so in 3 dimensions, you could actually, in order to have this bound, you don't need the u decays. You could be constant or you could be even slightly increasing. This is not expected, or at least this goes a little bit, I mean, surprised me in a positive way, but this is the decay character that helped with this. And this is obviously nice because also when Charlie was doing this simulation, he was always taking energy constraints. So he was fixing the energy and so on. So in this, at this level, that's why we were happy about it. but it could also even slightly increase in 3 dimensions. In 2 dimensions, it cannot. It has to decrease in order to get this this result. Okay, so this was just to wrap it up. So in Rn, clearly, there is no exponential mixing. It's polynomial. Right, so I forgot what I wanted to tell you. No, okay, so there is no exponential mixing, and this is clearly visible. And maybe I'll remember what I wanted to tell you, but I thank you for your attention.
Hi, I had some possibly very naive questions about the beginning of the talk. Can you go back to the first couple of slides where you contrasted advection with, yeah, go back, really the almost, okay. So, no, I thought that was very interesting. So that's just from diffusion. No, excuse me, this is just from advection.
So the first molecular. So
yes, I understand. The one on the bottom is from advection.
this is only pure advection.
Yes, I understood that. And go on to the next one, please. Okay, and this is with diffusion.
Yeah.
Is it the same U? It's the same velocity
same.
field?
The same.
Oh,
Exactly
so
the same.
yeah, okay. I thought it must be. Oh, okay, that's
the same.
oh.
No, I think the times are not the same.
Oh, so it,
Yeah.
And the level of cutoff level. So
oh,
the dark is the same degree of fixity in dark. Is it the same value in both?
Yeah. The same initial
So-
data. Exactly the same.
Yes, that's
Well,
what
but-
was it high. Yeah,
It's he has to. They have to.
because what is down there would be just white or gray.
okay, so you're not saying that you get less mixing when you have diffusion.
No.
That's what I found so strange.
No, so the thing is that if you would keep on running the simulation, you'll get stuck to a scale, and at some point nothing happens anymore.
And then I had another naive question, but I'm not sure I remember. Yeah. I had another naive question, but maybe I won't remember what it is. Can you go forward just a tiny bit more? And then I'll see if I get to it. No, back maybe. I probably won't remember what it is. No, we'll just. Yeah.
But I mean, I think I'm surprised there's one word that doesn't appear in your talk, and that's eigenfunction, right? The big difference between those two pictures of Charlie's is that if there's no diffusion, there's no eigenfunction, and if there is a diffusion, then you can sustain an eigenfunction, and where we're seeing that picture is the fact that there's a well-defined eigenfunction with a well-defined length scale, right? So I mean, have you considered? Does that help in any way? Like, because if you can prove that there's an eigenfunction, then the definition of lambda kind of follows immediately, right?
What does it mean there's no eigenfunction?
There's no eigenfunction in the sense that there's, yeah, there's no, there are eigenvalues, but there's, take a matrix that's lower triangular, right?
Yes.
That doesn't have any
So
eigenfunction.
It's just generalized, it's only that generalized.
That's right, yeah. So it's the same way, because you decay, but I guess I'm saying if there is an eigenfunction immediately, or if there is a slowest decaying eigenfunction, right, well defined in a way, does
Yeah,
the
but,
definition of lambda follow immediately? Because then, like, does that limit follow? Is what I'm wondering, right? Because if I can write the solution as something e to
I mean,
the minus lambda t.
Intuitively, yes. The problem is that I mean, okay, so maybe for specific application,
Right.
yeah, we can do it. Probably physicists already
Right.
have seen, I mean, they see the Batchelor scale clearly, but I mean, at theoretical level, so
It doesn't help to know that,
No.
right? Okay. Yeah. That's what I suspected. Thank you.
I thought of my
Oh,
second,
question.
my second question was, you wrote grad inverse at one point? Oh, sorry, what's a grad inverse?
So with the grad, you in Fourier space, you multiply by k, by the
Oh.
frequency, and then now you divide by
Yes,
k.
yes, yes, yes.
So
No, okay.
You
yes,
want
I
to see
understand.
the large scale.
But you, and you do the, what you have to do with the vector.
Hmm.
Yes, okay, right.
Hey,
Anybody else?
I guess I had a comment regarding what Jean-Luc just said about eigenfunctions. I did a bunch of these simulations on the torus after talking to Charlie and you, I guess. And the thing I was seeing, if you scale it correctly, is time periodic behavior. So I'm not seeing an eigenfunction. I'm seeing a length scale. I'm seeing some behavior that's time periodic, right? But so it's not, so I don't think there's an eigenfunction, but I still believe this length scale exists.
With diffusion, right?
With diffusion. I could not
Sorry,
hear
I
you.
guess I meant eigenfunction in the Floquet sense, right? So there's a decaying thing, but then there's also a periodic part.
This
that's-
might very well be true
Yeah.
in the torus.
Yeah,
But
exactly. So
could
I think
not
it's a
prove it.
Floquet, it's a Floquet eigenfunction. It's not, you know, it's slightly generalized from just an eigenfunction, but yeah, that's what
I
I
could
meant.
not prove it. All right.
Hmm.
The in-person or the virtual audience? Okay, so let's thank our speaker again. Thank you. I think we have a coffee break.